This is lecture 5 for data mining. If you're playing along with the homework assignments, now a few of you turned in homeworks to me, so I don't have any resources to grade homeworks for Googlers, but I will put the solutions up so you can look at the solutions to those. And I'm going to put up the chapter 3 homework. Actually, it's technically chapter 3 part 1 homework because I think some of that will spill onto the next one. And also, that doesn't pertain to you, but it is the chapter 3 homework is linked from the same place as the first homework. Now you just have to scroll down to see the first homework. And so if you're interested in following along with the homeworks, I will post solutions to that. So last time we were into chapter 3, which is exploring data. Now chapter 3, it's divided into section 2 basically deals with summary statistics, and section 3 deals with visualization. And I want to start with the visualization, and again, I think I said this last time, but I encourage you to also start with visualization. So the first time you get data, the first thing to do isn't to compute a mean for every column or compute the median for every column or anything like that. The first thing to do is to sort of maybe make some plots and sort of see what's going on in the data, because you might realize that half of the data is corrupted once you make the plot. So I usually start with the visualization, and so we're going to do that as we go through this chapter. And you can see here some quotes from the book about visualization, and I think the last point is probably the most important one. The goal is the interpretation of the visualized information by a person and the formation of a mental model of the information. And that's true not only for you as you're exploring the data, but for as you're presenting it to other people, you want them to be able to form a mental model of the data. So this simple toy example I started off with, which was just these 40 exam scores. And with 40 numbers, you know, you just look and you see, okay, I see 40 numbers. You can't really see anything about the distribution. Are there any patterns in the distribution? You don't really see anything. So of course you can imagine with 40 million numbers, you're going to see even less. At least 40 numbers, I can put them all on the same screen, but that doesn't mean I can really see anything interesting about the distribution. So the first thing we did, which was what your book talked about, was making a histogram, which basically just takes the numeric attribute, bins it into equally spaced bins, and gives the counts for each one. And I'm just going to go through these commands again, because I'm going to need some of these objects as I expand these things. So the first thing was to read in the data, which of course will give me an error because I have not set my working directory, and I'm just going to use my desktop again today as a working directory. But usually when you write scripts, you can set it to be whatever, usually set it to be whatever directory the script is in, but of course then if you move it, you have to change it. So let's see, I set working directory to be my desktop, and just tell Windows that the slashes actually go the other way. So I'm going to leave it as my desktop all day today, and now I can read in, let's see, read in the data set using the read.csv. Again, this one doesn't have a header. I'm going to show you one later on today that does have a header, but that one does not. And then we made the histogram, and again, the hist function just automatically returns a histogram. And I set the bins to go, you see here I set breaks 120 to 200 by 10, and so that was a histogram. And with that, I can see a lot more than just 40 numbers. I can see that what was going on is that you had a lot of people that did bad, a lot of people that did well, and not too many people in the middle. So there was sort of this bifurcation or this bimodal nature of the distribution, which you certainly couldn't see by just looking at 40 numbers, and you certainly wouldn't see it if you looked at 40 million numbers. Now, whether or not this is real, you know, well, let's just sort of see if it persists as you get more data, because it could sort of be an artifact of how I did the binning. But it's quite possible it's real, and if you had a whole lot of data, then you could be more confident that it was real. So that was the histogram. Then we said sometimes you don't want to have to make these bars, these solid bars. You want to make just points and connect them by lines, and obviously you can display the same information as the histogram with points connected by lines, and we said that was called a frequency polygon or a relative frequency polygon. And there's no function in R necessarily for doing that, but the way we did it was we took the histogram function and we sort of stole different parts of it, right? So the first thing, I do my histogram, and I basically make a histogram, but I say plot equal false. Okay, so it's not going to plot anything, but it's going to give me back some things that I want. In particular, the counts basically are the numbers indicating the counts in each category, and then the breaks, basically the 120, 130, 140, etc. are right there, right? So now I have the counts, and I have the breaks, and when it comes down to it, the histogram is nothing more than a plot of this on the x-axis and this on the y-axis. Now actually what I want to do is I want to use the midpoints of these, because that would be the point in the middle of the bar, and then I'll use those counts, and so that's going to be how I make my polygon. And the last thing here, let's see, I already called plot? No, I didn't call plot yet, so let me call plot. Plot, the arguments to plot are basically x and y, right? So maybe I'll just write. So when you call plot, it's a nice generic function in y. First argument is x, second argument is y. These are vectors. They have to be of the same length, obviously, because it's going to make a scatter plot with that. And so that's what I did here. My x values are 115, comma, breaks plus 5. So that would be 115, 125, 135, et cetera. And then the y values are the counts, but I added a 0 at either end because I like to make the frequency polygon go back down to 0. And then the only other thing left is to connect those points with lines. And so I did that by calling the lines command here. And then it makes my polygon have lines on it. And I think last time I put these up on the same screen along with the histogram, and you can see it's nothing more than the histogram, except I put points in the middle of bars, and I connect it back down to 0 at either end. So that was our frequency polygon. And I said one of the advantages to that was that you can put multiple groups on the same plot, and I'll do one of those today. Before I do that, I just want to finish up. The last thing I did last time was to talk about the empirical cumulative distribution function. So, you know, the histogram, the polygon are nice for looking at the distribution, but if you want to look at the cumulative distribution, that's going to be a monotone increasing or at least non-decreasing plot, starting at 0, ending at 100%. And for each value on the x-axis, you have the percent that is less than that value. So technically speaking, the cumulative distribution function gives you the probability that a point is less than a value, whereas the empirical cumulative distribution function is based on the data, so it gives you the percent of points which are less than that value. But of course, the empirical cumulative distribution function is an estimate of the real cumulative distribution function. Sometimes this plot is called an ogive, although that's not in the book. And someone wrote a really nice function, E, C, D, F, and R, that makes these for you. And so I think that's actually how I did this one, right? And I just call it here. I changed some of the defaults just to make it look a little bit nicer, but the actual computation is fine because how do you do this? Basically, every time you see a score, you go up by 1 over n, and the places where you see a little bit bigger jump, there's probably 2 of the same value in the data set, so it goes up by 2 over n, and then you're left at 100% or 1.0 on this graph. And so how can you use this? Well, you can say, you know, what is the median? Well, trace 50% over and say, okay, it's about there, like 165. What is the 90th percentile? Trace 90% over, it's down here, like around 190. What percent of people got less than 180? Look at 180, trace it over, and get 0.6. So that's sort of useful. But where this graph is going to be really useful, which is what I'll show you in a second, is when you want to compare multiple groups. And these graphs are really useful for comparing multiple groups, because right now it's just a summary of the percentiles, which I could just calculate. But for comparing groups, this graph will be very useful. So let's see. I think that catches us up to where we were last time. Yeah. So any questions on any of that? That's all from last time. Okay, so I did want to go through that just because some of those objects I'm going to reuse today, so I have them in R. So the question is now, what if I get sort of a second exam, right? If I'm teaching a class, I gave one exam, now I gave a second exam, and so I have second exam scores. So the question, you know, that you might ask is the second exam harder than the first or easier than the first? Now, because you're comparing two groups of numbers, it's not a simple question like just comparing two numbers, right? I mean, obviously, there's people here that are higher than some of the scores from before. There's some of the scores from before that are higher than some of the numbers here. So it's not sort of, you know, apples to apples comparison. There's also 3 people here that didn't even take the exam, right? There were 40 scores before. Now there's 37 scores. So the question of, is this exam harder? You know, we have to sort of think about how we're going to answer that question. So the short answer is that I'm going to go through some of the plots I made before and just sort of put them on the same graph. Now, the histogram would be tricky, right? Because you can't really have bars on top of each other. Moreover, you should make sure if you use the histogram, it has to, of course, be relative frequency. Because if this one has 37 and the other one had 40, you don't want to compare counts to counts. You want to compare relative frequencies to relative frequencies. So I should divide the total counts by 37 here and by 40 before. But again, it's hard to put histograms on the same graph. So polygons are even better. And you can use a different color type line for each group and then give a legend, and I'll show you how to do that. And so that's sort of useful for comparing the two groups. But what's even better is going to be to make the empirical cumulative distribution function and put both of those on the same graph. And again, you can also give a legend for both of those. So I'll show you how to do this, and I'll mention some cases in which these will be useful. So the first thing is to make the polygons on the same graph and give a legend for that. So first of all, let me, you know, I never made a histogram for these new scores. So let me read in these new scores. Let's see, close this guy. So the new scores are here. So this is more exam scores. And it's just, again, a single column, and the last score is 132, which is the last score. Then I'm going to make a histogram out of these new things, but I'm going to again say plot equal false because I do not want to plot it. I simply want to get the counts and the breakpoints out of there. So that's the same as before. Again, I don't want to overwrite my old counts, so I'm going to call these things new counts, and I'm going to call these new breaks. And if you notice, the only thing I really did different here is that the x-axis, I'm going from 100 to 200 by 10. Before I started, I think at 120, but there's some people that got lower. So if you were trying to automate this, here I just hard-coded these numbers, but in reality, you would somehow choose the min and the max, or let it do it for you and just make sure you're keeping track of what it does. And so I have new counts and new breaks, right? So the new breaks should go 100, 110, etc. And the new counts tell me how many are in each one. Okay, so that's enough to make a polygon. So let me do that. I basically plot the new breaks on the x-axis, the new counts on the y-axis, and there's my polygon, right? So the only thing I need to do now is connect these points by lines. Now the one thing you might wonder about is I had to set the y limit argument. And the reason I had to do that, right, I set y limit going from 0 to 0.3. The reason I had to do that, R will set the y limit by default, but if you look at the old polygon, right, this one, the frequency went up to 12, so the relative frequency would be 12 over 40. So I need to make sure my plot, which is going to later have this one on it, also goes up as high as 12 over 40. So that's why I set this one to go from 0 to 0.3. And then the last thing to do is to connect those points by lines. Again, the lines command works just like the plot command. You give it x and y. The only thing is, of course, this one makes lines and this one makes points. Also, this one just adds to the previous plot. So when you call this one, you get to set a lot of different parameters, like the labels, the margins, the x-axis label, the y-axis label, the title. Whereas this one, you don't get to set as many parameters because it's just going to add to this one. Okay. And by the way, if you make lines that are out of the limits on this one, it doesn't really complain. It just doesn't draw them. So I'm going to add the lines to this polygon. And then I'm kind of halfway done because I have the exam 2 scores plotted on my polygon. There we go. And you notice one other thing here. I'll say PCH, sorry, wrong thing, LTY equal 2. This is line type. 1 is the default, 1 is solid, 2 is a dotted line. Now, I will use, so here, I'll just show you the one up here. Oh, I will use different colors. But I don't know, sometimes people print things out on black and white, so you don't want to just use color to differentiate. Sometimes you also like to use different line types. So you could do thick versus thin. Here I made a dotted line. And so you see this is basically the distribution of exam scores for the second exam. We have a little bit more mass over here. A few people did really bad on the last exam, but most of the mass is concentrated here. And so what's going to be interesting then is to overlay the first exam and see how that compares. And so that's exactly what the next set of commands do on the next slide. Basically, I still have the breaks and the counts in there from before, so I'm going to add points with the breaks and lines. So points is sort of like plot, except it's not going to create a new plot. It's just going to put points there. And then lines, of course, the same thing. So it's going to put these points and these lines on top of the same graph. I'm going to make it blue and the default line type, which is solid. So I have a black dotted line, so now I'm going to have a blue dotted line. Sorry, I have a black dotted line, now I have a blue solid line. Notice in each of these, here I took the counts divided by 40, and the previous one I took the counts divided by 37, because I'm trying to make this a relative frequency and not frequency, right? I want to scale these things to be on 0, 1 to make it a fair comparison, because one exam had 37 people taking it, the other one had 40 people taking it. So let me just push in these last few commands. So this should just add points, right? It's just like the command plot, but it's just going to add to my graph as opposed to create a new one. So I've added these blue points, and now simply connect them by lines, solid lines. So I do that, and there's the solid lines, and then finally a legend. The legend command is sort of a very nice command to use. You see here I put a legend, and it tells me that exam 2 is the dotted black one, exam 1 is the blue solid one. The legend command is pretty intuitive to use in terms of the arguments that it takes. Basically, you give it x, y. These are the x, y coordinates of where you want the legend to be, and you might want to move it around, so it doesn't run into your graph. Or you might just want to create extra space on one side of your graph to sort of put it in there. Then you tell it what two things or what three things or what vector of things you want to assign the legend for. So this will be literally the text that appears on the graph. Then the color, this would be a vector. Exam 2 is black, exam 1 was blue, so I give it that vector. The line type, exam 2 I used a dotted line, exam 1 I used a solid line. And for both of them I used the plotting character equal to 19. So instead of giving it a vector of 19, 19, I just say 19 and it'll make them all 19. But you could make that a vector if you wanted to use different types of dots for the two different types of lines. And so then here you see the final product, and there's your little legend, which looks better here on my higher resolution. And you can compare the two exam 1 and exam 2. Now, it's not that easy to compare them, right? It's not that easy to see what's going on because, well, more people here, for exam 1 than on exam 2, but then this is really low here and this is really low here. And what you really want to say is, is one of them harder than the other, right? Did people do better on one exam than the other? And it is kind of hard to compare when you're looking at the whole distribution like this. You might make a case that exam 2 is harder, right? Because it certainly has more mass here, and less mass here. But then it has more mass here and this. So it's a little bit hard to compare. So there's other ways if you want to just compare two distributions, and one of those will be to plot the empirical cumulative distribution function, which I'll show you next. But this is one way to sort of look at both of the distributions on the same plot. And the nice thing is, here I noticed that exam 1 is sort of bimodal, where exam 2 really is not at all, although it does have sort of a few people that did really bad out there. Okay, any questions on making the polygons on the same graph? Okay, so like I said, this is sort of useful for comparing the two exams, but what would be really a lot better is to make the empirical cumulative distribution function on the same graph. So that's what I do here in 11. And the first command here, basically exactly as it was before, I don't think I changed anything here. So this is just going to give me the empirical CDF for the first exam, right? And that's what it was. So I think the only thing I might have done differently, I would go from 100 to 200 in anticipation of putting the second exam on there, which has some lower scores. So go from 100 to 200. That's the empirical cumulative distribution function for the first exam. And what I want to do then is basically add the second one. So now the function engEDU, remember, this thing I have to call it, here I call it within plot, and it'll create a new plot with that. It turns out I can also call it within lines. That actually is legal. It also works. Whoever wrote this function gave it the capability of being called within lines. And so doing this is simply going to add to this plot. I'm going to plot the more exam scores, where this was the first exam, this is the second exam. Again, verticals equals true. I like it to put the vertical lines. This is the dew points. I don't like it to put points, I put false. Horizontal lines are red, vertical lines are red. LWD, that one is the line width. LWD equals line width. 4 is pretty thick. The default is 1, which will be thin. So this one's going to be a red thick line, whereas the default's going to be a black thin line. And then when I put my legend, I'll say that. I'll say exam 1, exam 2. Exam 1 is black, exam 2 is red. The line width, I give it a vector, right? Exam 1 is line width 1, which was the default. Exam 2, line width 4, which is what I specified here. So that should do the trick. And then the interesting thing is going to be what we can say about this graph once we make it. So I do this. That gives me the red line, and then I do this. That gives me the legend. And now I can, where'd the legend go? Hello, where's my legend? There it is. Okay. So now I have the two exam scores. I have their empirical cumulative distribution functions plotted on the same graph. The y scale is always going to go from 0 to 1, but you just have to make sure you get the x scale so you get all of them. And so you see, here's those 3 people that did really bad on exam 2, right? 1, 2, 3. Those are the 3 1/n jumps there. And then, you can see. Now the interesting thing is that the red line is always above the black line. Okay. So does that tell me that exam 2 has higher scores or lower scores? Lower scores, which is a little bit counterintuitive, right? The fact that the red line is on top means the scores are lower. And you have to be a little bit careful with that. But if you think about it, it makes sense, right? Because if you look at anything here, right, like 140, well, for the exam 1, a small percent got less than 140. But for the red line, a larger percent got less than. So we're always plotting the cumulative percent less than, right? And so that's what happens is like being on top means you have lower numbers overall, right? What's the percent that got less than 180? Well, a higher percent got less than 180 on exam 2, which means they have consistently lower scores. So what this is showing you is that every percentile, every empirical percentile for exam 2 is lower than the corresponding one for exam 1, right? Every single percentile. So in this case, the terminology is one distribution is stochastically larger than the other distribution, right? It's every percentile you line it up, you get a larger value. So this is sort of, end of story, right? You don't have to really worry, well, some exam 2 scores were higher than some exam 1 scores. It doesn't really matter. Every percentile for exam 2 is lower, so I can say sort of unequivocally exam 2 was a harder exam. Okay, you have a question?
So another way of looking at this might be to say that the red line is to the left.
Yes,
of the black line.
I think that's more intuitive.
To the left is lower score.
Right, they're both here, and the red line is shifted to the left. So it would be as if I had, a distribution here, and this was the mean, and then exam 2 shifts to the left. Okay, and the nice thing is, if the distribution doesn't change shape, these two lines will never cross. If you just do a shift of location, it'll exactly shift the location here. The lines will never cross, right? Okay, but if the lines do cross, then the story is more interesting, right? If you say, well, I don't know, more interesting or more unappealing or something, but they always start at 0 and end at 100%, right? So let's call this 100%. Okay, so if the next line crosses, let's suppose, here I can try and match the colors. Suppose the red line here, started off higher, right? But then at some point it crossed. Okay, at some point it crossed. So now certainly I can't say one exam is sort of, just harder than the other, but I do have to say that, for the exam 2, this part of the distribution is consistently to the left, but the very highest, like maybe the top 10% of exam 2 people actually did better. And so you can't really give one answer to the question which exam is harder, because the top, maybe the top 10% of exam 2 scores are actually higher than the top 10% of exam 1 scores. And so this type of thing comes up if you imagine, suppose this is something more interesting. Suppose this is like latency. So you've done some experiment where like you've decreased latency for most of the distribution, but the 10% longest latency cases are actually worse. So do you actually want to launch such a change, right? Because for 90% of the people you made the experience better, but for the worst 10, you made it even worse. Do you really want to launch such a change? So you have to think about that. So if one completely dominates the other, it's clear cut. If you have them crossing, then it's not so clear cut. Okay, you had a question.
Yeah. Could you maybe move the whiteboard over to the other side of the room so it's not blocked by the
Right.
stand?
So that's related to the other problem, which is I'm supposed to stand here all the time because this microphone only works and this one doesn't.
But it kind of seems that you have been far enough away from
Yeah, that's a good idea. Let's do it. If we get in trouble, it's your fault. All right, there we go. So there's now a whiteboard over here, and this screen has the same thing as that screen, so that's
So
it.
I also have a question about the differences between those two. For situations like this where you just have two distributions, wouldn't it be a little bit more rigorous to do a test for statistical equivalence to see if there's any significant difference between the two of them?
Right. So one thing is like a lot of tests would be based on a normality assumption, right? So if you did like a 2-sample t-test, it's based on a normality assumption. So, do you believe the normality assumption? Well, then you should first look at some QQ plots and see if that's legitimate. If you don't believe the normality assumption, then you have to use some sort of a non-parametric test, right? So, yeah, if you really want to do that, but the question is like, the question of statistical significance really comes to your sample size, right? And in this case, arguably, I have the whole population. So there's no notion of statistical significance. If I say this is the whole population, 37 and 40, right? Because statistical significance is saying, is your sample large enough to justify generalization to a population? But if I say 37 and 40 is my population, then I don't have any generalization. I'm just saying my students did better on the first exam than on the second exam.
What about the three that didn't take the second?
We're going to talk about them. Yeah, they're interesting. And it's cute that it never complained about those three, right? And I'm going to talk about that in a second, because we kind of wish it would have complained a little bit about those three. So we should talk about that. Okay. There was another question, maybe?
No, it's also about the other three.
Yeah, we should talk about the other three.
When you talk about the 37 or 40 being the entire population, is that, but somehow I feel that that's not quite
Right. So there's the question of, yeah. The question is exam 1 harder or easier, or did the students do better on exam 1 than exam 2? If I'm just sort of doing descriptive statistics, maybe it's the latter question I'm after. But if I'm interested in inferential statistics, I might want to view my 37 as a sample, view my 40 as a sample, and of course then the right thing there is that I'm really losing a lot of power if I don't really associate the student with the exam and treat it as paired data, because really then it should be a paired t-test where, with 3 observations dropped out. So yeah, so I'm not really doing this to talk so much about the statistical inference and whether or not we can generalize this to a population. And if you were doing that, there are tests that are appropriate. I'm doing this more as a descriptive exercise to just sort of visualize the 37 versus the 40 students. And in data mining, right, often it's not so much generalization to a larger population that you're after. It's understanding all the data you have, which might be effectively the whole population. But it is a good point that the inference versus the descriptive should not be too confused. And this is merely a descriptive exercise, and we haven't established any statistical significance. OK, other questions on this exercise? So basically, we're looking at the 2 cumulative distribution functions simultaneously. One more question.
A legend again with a different location parameter? Is it going to
Yeah. It will just plop out a new one. So you want me to call legend and like move it over to the left a little bit. It will just annoyingly put, right? So
then how do you, experiment? Oh, you have to.
Yeah, you start over again, right? But if you're saving your commands, then it's just a matter of putting them all back in again and trying a new legend. But I think you can see where it's going. It's going, what did I call it, 120.6? So I think it's the upper left corner. The question is like how big it is kind of depends on your display, and so that can sometimes get messed up a little bit. But yeah, 120.6 looks like the upper left corner. So it's not completely random, but yeah, you might want to have to experiment. Any other questions on this plotting exercise? One more in the back.
Is there a way to plot the difference between the 2 distributions independently?
Right, so the question is, can we plot the difference between the 2 distributions independently? And I'm going to do that in a second, but when you talk about difference, it's almost at the student level, and in that case, I need to sort of know which student took each exam, right? Well, I mean, you could plot differences in percentiles, but what I'm going to do is next associate the students with the exam and visualize that sort of, and that makes for a nice picture if I know which student took each exam, right? But yeah, you're right. If you didn't want to plot 2 CDFs, you could plot the difference in 2 CDFs, but it would be hard if you had 3, right? So that works well. OK, so let's move on to the next thing, which is, OK, I already answered this question, right? So based on the plot, which was harder, which had lower scores? Well, the second exam had lower scores because it was higher, or as we said, probably better to say it's to the left. OK, so far, exam 1 and exam 2 data, they were on the same scale, but they weren't paired, meaning I didn't know which student had exam 1 score and which student had exam 2 score. I didn't have any association between the 2 exam scores. But a lot of times we get data that's paired, and when does data that's paired come up? Well, so here's where I get in trouble. So data is paired in the following situation, right? Basically, if you think about the chapter 2 idea of data, which was this matrix with observation 1, 2, 3, 4, the different observations, and then we had different attributes, attribute A, attribute B, attribute C, etc. So if I just take attribute D, if I just take any 2 columns, right, take attribute A and attribute C, that data is paired, right, because both of those are for observation 1, both of these are for observation 2, both of these are for observation 3. So when I have data like this and I'm comparing 2 attributes for the same data, I have a paired relationship because I can tie these together. And I haven't done that, with the previous 2 data sets, right? I had just 37 scores, another 40 scores, and I just compared them. But this third data set I have linked up here, exam scores and names, actually does pair the data together. It actually tells me which student took which exam. And I can show you exam scores and names, right? So I don't have real names up here. They're sort of generic names, student number 1, student number 2, etc. And then I know that this first exam score, 192, from exam 1, and the first exam score, 187 from exam 2, actually go with the same student. So then how do you explain the fact that one has 40 and the other has 37? Well, right here. This is what some of you asked about. This guy, he didn't take the second exam. He somehow dropped out of the class. And so same thing here and same thing here, right? So the students who took exam 2 is a proper subset of the students who took exam 1 because I have 3 missing values here in exam 2. So that's paired data, right? Because these two numbers go together, right? They go with student 1. The next two numbers go together. So what can I do with paired data? Well, of course, the most obvious basic thing is the scatter plot, which I think is, my favorite plot, right? The scatter plot can often reveal many, many interesting things. And of course, the plot command in R is basically producing a scatter plot. Points on the X, points on the Y, it makes a scatter plot. This is talked about in your book on page 116. There's some examples in your book. This is interesting to talk about in terms of large data sets. It says when the data has 2 or more numeric attributes, right? We're plotting numeric attributes. You can make scatter plots of all possible pairs. And the function pairs in R does that. So some people I know, the first thing they do when they get a data set, and when everything's numeric especially, they type pairs, they look at all the scatter plots. Now, if you're thinking about large data in a lot of attributes, p choose 2 could be a large number, and you can't look at all possible pairs. So, really, if you have a lot of attributes, you might want to look at certain pairs, a random subset of pairs, pairs with the highest correlation, pairs with the lowest correlation, etc. But, for just a small number of attributes, sometimes people use this pairs command. And your book calls this a scatter plot matrix, and they talk about it on page 116 if you want to see that. So that's sort of nice for sort of visualizing all the pairwise relationships between the numeric attributes simultaneously. So of course, the thing I want to do is to make a scatter plot for my exam scores. And that's what I do here on the next one. Now, R by default is going to scale your X and Y for you according to the min and the max. But because both these exams are on the same scale, I want to scale X and Y both the same. So I'm going to go 100 to 200. And I'll show you how to specify that. Also, some people like to add the regression line. I often, though, just like to add the diagonal line, just so you can see who falls above and below the diagonal. And then we'll see what we can see on the plot. So let's see here. So I have the data read command. And actually, I'll paste this all in at once and then tell you what's going on. So here's basically read the data in. Now notice the interesting thing here is what you don't see. You don't see header equal false because in that data set, I have column names. So what it's going to do, it's going to take the first row, right? The first row in the CSV file are these 3 names. It's going to use those as the names. So later on, I can say data $exam1, and that'll call column 1. OK, so that's interesting to note. Then plot X comma Y. Now notice actually data $exam1. If you notice the name in the CSV file is exam space 1. R, of course, doesn't like objects to be named with spaces in them, so it changes the space to a dot. And then exam.2 on the y-axis. X limit 0 to 200, y limit 0 to 200. PCH equal 19, right? That's what I live by. That's the solid dot, right? Not the default open circle. This one I like a lot better. Label the title, X is exam 1, Y is exam 2. And then AB line, I haven't showed you this command before, but the function AB line is good for making sort of like, in this case, a diagonal line. You can call it a couple different ways. What I'm using is the intercept slope, right? Did I get that right? Intercept and slope. So if I say AB line 0, 1, that's a line with intercept of 0, slope 1, that's the diagonal line. You can also use it for horizontal and vertical lines. Vertical lines especially useful if you don't want to say an infinite slope, so you just say h equal or v equal. But here I called it with AB line C 0, 1, intercept 0, slope 1, makes a nice diagonal line. And so this should give me a nice scatter plot of my exam scores. And you can see here, well, it's better if it's like a square display, right? So let me try and leave it square. You can see here that what's going on? All but 2 people are below the diagonal, which means what? Means all but 2 people did worse on exam 1 than they did on exam 2. So this is when I say that the data is even more powerful if you can pair it. Because just to say, oh, all the percentiles are lower, everything like that, well, whatever, but on a case-per-case basis, you've eliminated the person-to-person variability, and on a case-by-case basis, consistently, everyone did worse on exam 1 than exam 2, with the exception of these 2 people. And speaking of statistical inference, which you guys started talking about,
Better on exam 1.
sorry, yeah, I probably say it backwards half the time. Better on exam 1 than exam 2. Worse on exam worse on exam 2. The right inference once you have this data would be to use a paired t-test and just look at the differences and do a one sample t-test on the differences. That has more power than the independent sample t-test for this case. Okay, so then these two guys are of course interesting because they actually somehow did better on exam 2. These guys are sort of everyone, you know, but you might want to know who's doing really well. And then these are sort of the three guys that did really bad on both exams, but especially bad on exam 2. And you know, this is a nice scatter plot. I really see what's going on in the data right away. And so when you have paired data, this is useful. The only thing I sort of like to do beyond this is to sort of, you know, label the points in some way, or maybe use some color coding to reveal a third dimension. And that's really useful in R. Well, in terms of color coding, I won't show you that, but you can pass a COL argument and give it a color vector, the length equivalent to the number of points, and you can make each one a different color. So you could color, you know, the boys blue and the girls red, or the seniors red and the juniors green, or, you know, whatever, and just sort of see that at the same time. I won't show you that, but what I will show you is how to label the points. And in R, there's a couple of cute commands for labeling points. So there's my scatter plot. Text and identify are very useful for labeling points in the scatter plot. So text is the one that basically, if you just call text, it'll label all the points, or you can specify certain points to label. Identify is sort of a more interactive point and click thing if you're just playing around, where whatever point you click on, it'll label it for you. Okay, but of course, it's hard to sort of automate that. So sometimes you use this just to figure out who they are, and then you use text to label them. And so let me illustrate both of these for you. So I want to use the text command to label everyone who got less than 150 on the first exam. And then I'm going to use the identify command to sort of pick out the two people that did better on the second exam than the first exam. And then I'm going to use the first column as the labels, because if you remember, what is this thing called? Data, first column. That's the student names, right? And in fact, I can refer to this as data, $, whatever it's called. I think it's called, let me cheat, data, $, student with a capital S, student. That's the first column, right? That's the student names, data, $, exam.1, that's the first exam, etc. Data, $exam.2 is the second exam. Now, one thing that's real interesting here, right? And we talked about this a little already. There are 3 people that never took the second exam, right? And those 3 people, let me come back a second here, they don't show up, right? They're not here. And so it's interesting that R never complained about that missing data, right? It just, the NAs just passed through there and it never complained because the default behavior in plot is NA omit. But you know, that's interesting. And 3 out of 37, or 3 out of 40 rather, not such a big deal. But if it was 50% of the data, you would like to know, and the fact that it doesn't complain is kind of annoying. So one thing, you know, people do sort of as a first pass on data is they see just how many missing values they have. And it might be curious, you know, where did these 3 people go? Are they 3 people that did really well here? Maybe the class is too easy, so they dropped out. Are they 3 people that did really bad? Maybe the class is too hard, so they dropped out. Are they 3 random people? It would be interesting, right? Anyway, we just sort of forgot about those missing guys. Okay, so let me show you text and identify commands. The first thing I'm going to do is the text. And basically this is going to, let me see if I can explain this. Here, first I'll put it up here. So this basically labels, it's kind of overwritten here. Basically it labeled the 3 students that got less than 150, right? 150 is there, it labeled these. How did it know how to do that? Well, let me put the command back up there. So text takes basically 3 arguments, right? X, Y, and then what the labels are. And the labels, you have to literally say labels. So basically what I did here, the shortcut, if you forget about everything in the square brackets here, data $exam1, data $exam2, labels, if you just called that, you would basically label every single point. Now that would make the plot look pretty messy, right? So what I did is I took a subset, and this is the same subset each time. It's data $exam1 less than 150, data $exam1 less than 150, data $exam1 less than 150. So this is not row numbers, but it's actually a logical vector. And if you just grab this part here, oh, sorry, I just want to grab this part here. Won't let me, will it? Okay, I'll put the square bracket myself. Just grab this part here. Oh, data $sign here. Let me just do this, no square brackets. There, it's just a logical vector. meaning, which people got less than 150, which people didn't. And in fact, if you look at $exam1, it's just going in order, telling you, this person did not get less than 150, not true, right? So it's just a logical vector. So when you subset on that, it will basically pick out the rows where this is true. So you can easily just pass the logical argument into the row, into where you would normally specify which rows, and that'll pick out the rows for you. And so I basically passed the same one in each time, and that selected those cases for X, those cases for Y, and those cases for the labels. And so then that has the effect of labeling everyone who got less than 150 on my scatter plot. And then as I showed you already, your scatter plot then looks like this, right, where you've labeled everyone who got less than 150. And so, you could write the script, and every time, you give the same exam, it's always going to label the student names for those people who got less than 150. So that's sort of the automated way to label points on the graph. Then the interactive way, which doesn't really, you can't really write a script to do this one, but if you're just playing around, you can use this identify command, which takes sort of the same arguments as the text command, but it's more interactive. And once you do that, it basically, so you see my window here sort of freezes, okay? And what it wants me to do is go over to my graphics window. And basically now, oh, sorry. Basically, it's a point and click thing here, right? So you mouse over the point, and it actually depends where you put the mouse. If you put it over here, it'll label to the left. Oh, it doesn't like my display. If you put it over here, it'll label to the left. And if you put it up here, it'll label on the top, right? So, and then how do you make it stop? You right-click and you say stop. Now, you can still, save this thing as a file, right? Those labels will be there, but you can't really write a script. I mean, this is just sort of the point and click thing, and wherever point you point to and click, it'll put its label there. And so that's sort of fun. You don't have to dig through the data to see who's who. You just say, I wonder who that point is. You click on it, and it'll label it. So that's the text and identify. And then one other thing that I really like about labeling points on the graph is the following. And it's sort of a subtle point, but I think it's important. When I tell you that when you make a graph, you want it to be self-explanatory. So I know this is exam 1, I know this is exam 2, but the thing is, whenever I see a graph, I always ask people, like, what are the points, right? Are the points, in this case, I know now that they're students. As soon as you label one of them as student number 30, you know that all the points represent students. But often I see graphs and I say, okay, so are these points URLs? Are these points web pages? Are these points search engines? What are these points, right? I know what the axes are, but I don't know what unit the point represents. It's possible, if you didn't see these labels here, exam 1, exam 2, the points could be professors, the points could be universities, the points could be anything, right? You want to know what the unit is. And I think by labeling at least one of them, then you start to know, oh, these units are students. And you actually know personally who a couple of them are, okay? So that's another argument for labeling points on the scatter plot. So let's see, what else do I want to say about scatter plots? I think the last thing I want to say about scatter plots is the following, okay? When you have a scatter plot, you never really see this problem coming until it hits you. If both of these are discrete, or even if they're not discrete, if you've floating points, but you've only sort of used, so much memory for them. So at some point you have at some point everything is discrete, right? We know that. So if they're discrete, and in fact I think arguably exam scores are, right? Because I probably don't give half a point. So if I give half a point, maybe I don't give quarter points. So let's assume these are rounded to the nearest whole point. So exam 1 is discrete, exam 2 is discrete. Well, if they're discrete, that means that points can hide on top of each other, right? Any one of these points could actually be 2 points. Now, when is that a problem? Well, it's a problem when I start getting a lot of data. We talk about data mining, on large data sets. You say, how large is large? Well, at some point, we're going to start having problems. And the point here at which we would have problems would be if I have a whole bunch of this data, what do I have? Eventually, I just have the whole grid from 0 to 200, and everything has a point. And I have no sense of where there's a lot of points or where there's a few points, right? And that's really what I'm trying to look at for this graph. I'm trying to see, oh, here's this relationship, right? Because there's a lot of points here. Well, if it's just all filled with points, and I can't judge sort of the density of the points in any region, I'm out of luck. So what's the solution with this discrete problem, the points lying on top of each other? Well, it's the simple sort of hacky solution, which is just to add a small amount of noise and just jitter the points a little bit. Now, the other problem, which is related to discreteness, but if you just have so many points that, then you just wind up with just a huge black blob, you still may need to do some subsampling, right? And if you do the sampling randomly, then you can still judge the relationship. So these two are a little bit related, but if you have small data and discreteness is the issue, the jittering will help. If you just have so much data that the scatter plot's just a solid blob of ink, then you might want to take a subsample. But let me show you this first case with the jittering, because this, of course, is really easy to do in R. Suppose I just want to add uniform noise to both x and y, uniform negative 0.5 to 0.5. Well, all I would do is overwrite exam data $exam1 and data $exam2 with the same thing, but R uniform generates uniform random numbers distributed on 0, 1, and this argument is 40, right? There's 40 rows in this data, so to each of them I add 40 uniform random numbers, and I don't want to do it on 0, 1, because that would be adding a positive amount to both dimensions, so I subtract 0.5, so that'll be uniform on negative 0.5 to positive 0.5, and then I do everything the same as before, and so, this will overwrite the values of exam 1 and exam 2. I mean, you might want to call it something different, just so you don't, add noise to your data and lose your data forever. But I'll just overwrite them and then go back and, let's see, get this here. And that will make the graph. And then, oh, shoot. OK, sorry. Don't overwrite the data. So fix it again. OK, sorry. Try one more time. Don't overwrite the data. OK, add the noise, go back, make the graph, don't get the data. OK, that'll make the graph without overwriting the data, and then go and get the text and identify commands. And of course, identify doesn't do anything until I actually click, click, click. OK, stop. OK. So basically, it's the same graph plus noise, and if there had been discreteness issues, they would have gone away. Let me illustrate this to you a little bit better on the PowerPoint. I'm going to take, here's my solution with noise. Let me go back then and steal my other one without the noise and line them up right next to each other and just sort of show you. Let's see. Oh, wait, that's not the one I want. I want the one with the labels in. Here we go. This one compared to this one. There we go. So you can see sort of the points just sort of dance around a little bit, right? And so had this point been on top of another point, once I add the noise, it moves around a little bit. If that's not enough, if they're still sort of smacked on top of each other, you could add a little bit of noise. But you see how they sort of just move a little bit. Now, the thing I think that's cute in this example when I did it is here I have 3 labels, and here I have 4 labels, right? 3 labels and 4 labels. So this student number 40, he was not labeled before, and now he is. What happened to him? Yeah, right? Before, I labeled everyone less than 150, so he did not get below 150, right? Maybe he got exactly 150, but as soon as I add noise to him, there's a 50% chance that he falls below, and so now he gets a label. So, the noise is non-deterministic, so don't let that bother you, and you can save the seed if you have to. But, like I said, it's sort of a hacky solution, but it sort of uncovers points, and so if you have a lot of people stacked on top of each other, you can see. And one case that comes up all the time is, maybe I can sort of illustrate this on this board, is that on the scatter plot, you're often looking for like linear relationships like this, right? Like obviously there's a strong relationship, positive linear relationship, right? But what you might happen, if everything is discrete, you just see like this, right? So let me here do the case of like 9 points, right? So you just see this, but you don't realize that 1 million, 1 million, 1 million, and like these guys are just 1 point. So you don't realize that it is a really strong relationship with all the data there until you sort of jitter a little bit to uncover that. So that's just the thing to watch out for.
Right in front of the camera. The whiteboard.
Well, why is
Thank you.
So you guys look at my back the whole time? Never knew that. OK. So anyway.
Could you aggregate the points and then sort of draw them at different fatnesses as well?
Oh, yeah. You can like do the bubble plot and set the bubble to be the density. Yeah, people do that too. And the bubble plot's sometimes useful for showing a third dimension also. Sometimes people do that. OK, so let's see. That takes care of adding noise. So I think, where are we at? The last thing I was going to talk about was the box plots. Let's see. Should I get into the box plots today? I think I'll just save that. Sort of, it's a natural breaking point. So I think I'll save that for next time. Do you guys have any questions before I take off?
What about those NAs? I mean, we haven't.
Yeah.
You said we'd speak again about it.
Yeah.
Can't I set something like an artificial score, like a 90 for the NAs and plot that?
Yeah, so I mean, you could, so the question is about the missing values, right? So we had these 3 guys that never took the score. I mean, all I know about them is their exam 1, right? And so I could, put a vertical line, I could put a predictive point, right? If you drew the least squares regression line, you could make a prediction for them, but they're just going to be right on the line because the best thing you would predict is the mean,
I'd
right?
just like to see where they are
Yeah.
by some artificial, I would say
Yeah.
90 because that's out of the range, so it wouldn't.
Right. My inclination would be, in terms of just displaying the data, to just put, sort of tick marks down at the bottom to indicate the missing values. And the thing to watch out for is, what if 90% of the data was missing? To just ignore that is, a bad situation. And, I think a lot of times when you deal with real data, the most interesting cases are the cases where the data is missing, right? There's something going on often.
There's a lot of practical issues with that. I mean, it's like, okay, let's look at how good these mutual funds are doing, and we basically are looking only at those who are still in business 20 years later, and all those that have dropped out are selected out automatically. So, oh, they did great. Right. Well, yeah, those 10% that survived. So it's like the students are going better and better, yeah, because
everyone else died. Yeah. Right. I think that'd be an excellent example, right? If exam 2 was higher than exam 1, it's a biased sample. It's the sample of people that stayed in the class, right? So I've got rid of all the people that were sort of on their way out, right? And if I had exam 1, exam 2, exam 3, and people are dropping out, then each exam could get better and better and better, right? So yeah, that's a very important point, that the missing values, a lot of the software just ignores them by default, but in the analysis, sometimes that's the most interesting signal, is why are people missing, and to appreciate the bias that you have because you're only looking at the non-missing data. Other questions about anything before we take off? Okay, so we'll finish up these notes on Friday.